And if you have any questions for James, please put them in the chat, and then we'll have a Q&A session at the end. And we will be prioritizing early career questions because this is an early career event. And with that, I'm going to introduce our speaker. So Dr. James Cecil-Keane is a planetary scientist at JPL. He studies the interactions between orbital dynamics, rotational dynamics, and geologic processes on rocky and icy worlds across the solar system. He has extensive experience with NASA planetary science missions, including Grail, New Horizons, and Juno. He served on the Mercury and Moon panel of the recent Planetary Science and Astrobiology Decadal Survey, and was the science champion for the Endurance mission concept. Dr. Keane is currently the Lunar Program Scientist in JPL's Solar System Exploration Directorate. So if you want to take it away, Dr. Keane, thank you.
Sure. Thank you very much. I'm happy to be here. Let me just share my screen. Okay. So hopefully you see my screen well. So yeah, I'm very excited to be here to talk about endurance. I've talked about endurance a lot since the last Decadal Survey, and I think it's a really exciting mission concept, and I'm hopefully going to convince you all that it is also a very exciting concept. And I'm going to try to hit on some of the points where to show why me, a geophysicist, is so interested in getting samples back from the far side of the moon. Okay. So I'm going to step through a few parts of this talk, basically explain the scientific rationale, then the mission concept, and the path forward. So, as you all know, being in Lunar Next Gen, the moon is beautiful and amazing, and we look up every night or sometimes every day to see the moon in all of its beauty. Endurance is a mission that's going to go to the far side. So this animation produced by Goddard is flipping us around to the far side of the moon with the Earth looming menacingly in the background. And South Pole-Aitken Basin is this large, dark region here on the southern far side of the moon, going from sort of the low mid-latitudes all the way to the South Pole. I'm going to turn off captioning for myself. Can't move that. Oh, there, I can move that. So it's this ginormous basin. And why is this giant basin so important? So SPA, which here you can see in this sort of synthetic view that I created, again, this dark region on the far side of the moon, is interesting because it is the largest and oldest undisputed impact basin on the moon. It's over 2,000 kilometers in size, dominating the southern highlands. And so while it's kind of hard to see in the albedo image or the color image mosaic of the moon, once you flip to topography, it just jumps out at you. So here's a topographic map where the blacks are lowlands, some as low as 8 or 9 kilometers below average, and the whites are highlands. And so you can see this enormous basin is just a giant divot on the far side of the moon. This is my favorite picture of SPA. This is a real image, unlike the last set of images. This was taken by the Discover spacecraft, which is a joint NASA and NOAA spacecraft. So most of the time it's observing the Earth and looking at Earth's climate. And every once in a while the moon photobombs it. And you can see SPA in this as the darker region on the southern half of the moon. So one of the reasons that I'm interested in SPA is just how enormous it is and the sheer consequence that that enormous impact would have had on the moon. So here's an example. This is a work done by Jordan Kendall in his PhD thesis at Purdue, looking at the formation of the impact basin. And so we think that the impactor was something like 200 kilometers in size, so a pretty large, probably potentially, oh my God, that was a lot of potentialities. A differentiated planetesimal that just smashed into the moon and would have excavated lunar mantle, lower crust, and splattered all this material on the far side of the moon. Giant impacts like this are interesting to me because we see them all over the solar system, and yet we don't really understand how they work. And so the moon is up here in the top left where you can see South Pole-Aitken. Now I've used blue and red as my lowlands and highlands in topography. You can see South Pole-Aitken Basin here, but giant basins of the scale of SPA either in the actual physical size in 2,000 kilometers across, or as a function of percentage of the body, dominate planets and moons across the solar system. So, for example, my other favorite large impact basin is Sputnik on Pluto, down here in the bottom right. It's about half the size of SPA, but kind of comparable in scale. And all these basins, there's a surprising lack of work in understanding how they form and how they affect their host planet, how they might impact, say, mantle convection or overturn, how they excavate material and deposit it on the surface, their role in heating of the body. There's all sorts of questions that sort of spin off from these giant impacts that remain unanswered. But one of the biggest drivers, the longest standing driver for going to SPA, is really about its role in understanding solar system chronology. So here I'm going to build up sort of a qualitative picture of one aspect of solar system chronology, and that's the impactor rate as a function of time. So on this little chart, I have today over on the left, 4.5 billion years ago on the right, so formation of the solar system, and some geologic timescales for the moon, Earth, and Mars down on the bottom. And as we know from analysis of samples and dynamical models, as you go back in time, the impactor rate goes up because there are more and more asteroids and comets around to hit planetary bodies. And by the time we get to about 3.5 billion years ago, we start reaching terrains that have been well dated by Apollo and Luna samples. But once you go further back in time to, say, 4.0 billion years ago, there you start running into a lack of samples that can definitively answer some of the questions, and you start coming up with competing hypotheses about what's actually going on. And so this is one of the classic hypotheses in lunar and planetary science about whether there was a spike in impactor flux around 3.9, 4.0 billion years ago, sometimes called the terminal lunar cataclysm or late heavy bombardment. And this is interesting because this spike in impactor flux would have had a huge impact not only on the moon, but also if you start zooming down here to the Earth, what's going on the Earth, which is only a short distance away from the moon. Life is emerging around this time. It's also the time when we have the oldest preserved rocks. Some of the very earliest geology is happening. And so it'd be really interesting to figure out what's going on in the Earth-Moon system around this time. And one of the ways to test this, one of the most desired ways to test this, is to go to impact basins on the far side of the moon to try to get away from the things that we've already dated and see if those impacts also sort of cluster around this age or not. Now, if you go further back in time, the models just become, they go all over the place. And this is where SPA actually is the most useful, because SPA, as the oldest basin, is your opportunity to sort of tie down all these chronologies at the earliest possible moment. And that's important not only for understanding the impactor flux, but it's also telling you things about the moon itself. So, for example, do we see every large impact basin on the moon? Has every large basin that formed been preserved? Or were there basins that were lost, say, erased by other craters or viscously relaxed away because the moon was so hot? What's the actual total impact record that we see on the moon? How far back does it go? And these are the kinds of questions you can start getting at with SPA, which is somewhere around this age. So the science of SPA is interesting, and I'm just highlighting a couple of the big ones, the big questions. But this has led to the realization that there are a lot of science objectives that we could do by going to the far side of the moon in SPA. And so here I have 5 boxes that show the objectives from Endurance, which are very similar to the objectives from past mission concepts to go to the far side of the moon. And they have things like figure out the age of SPA, figure out the age of these large basins, all sorts of other things. And the challenge with SPA is that it is so big and so diverse that it's hard to answer all these questions in one mission. And so, for example, here's again the topography to show you scale. If you want to date SPA itself, one approach you might take is to go find impact melt from SPA, or the differentiated impact melt sheet from SPA, and grab samples from that. And so the green shows one group's model for where some of that material might be, smack dab in the middle of SPA. Great. Now let's say you want to figure out the late heavy bombardment question. That you want to go to some large basins, here shown in the sort of cyan blue color. And you can see there are places where these craters overlap with the green, but it becomes less numerous. If you want to do things like figure out what the mantle is made out of, the stuff that was ejected from the SPA impact, then you want to go to the ejecta. Here is one metric that has been used to explain, or to try to trace mantle material, which is thorium abundance, shown in purple. And then if you care about, say, volcanic processes and how they're different on the near side versus the far side, then you might want to go to a volcanic deposit, for example, the Mare deposits on the far side, shown here in red. And you can quickly see that there's no single spot on the moon where you can confidently get all of these different terrains that you need to answer the objectives. You could probably pick one or two that get several of them, but not all of them. And so that's been one of the challenges for past mission concepts to go to the far side of the moon. So that's where endurance comes in. So just to take a step even further back in time, endurance was a product of the Decadal Survey. And so what is the Decadal Survey, if you are unaware? The Decadal Survey is something that is written, surprisingly, every 10 years at the request of NASA and operated by the National Academies of Science. And it's this big, it's enormous. I have my physical copy here. It's way too large. Document that is a consensus document designed to identify some of the highest priority science questions for the next decade. And it really sets the goals for NASA at the highest levels. And it's also a document that other agencies and other stakeholders, so like Congress, go and point to help figure out what things get funded. And a key part of this is that for the largest activities, the large missions, flagship missions, New Frontiers missions, which are sort of billion-dollar missions, it sets the specific targets and the specific goals for those missions. And I think it's also interesting to note, in the last decadal, I was just entering grad school. And 10 years later, I had the opportunity to be involved. So these timescales seem long, but it's not, they kind of blow by when you are busy with grad school and research. And so if you ever have the opportunity to participate in the Decadal Survey or a National Academy study, I would highly recommend it. I think it's a very illuminating process. And to highlight that even more, here's a little bit of the organizational structure of the Decadal Survey. I was in the Mercury and the Moon panel, which here is a Zoom screen grab of all of the people's faces. And these are some of the best people that I've ever had the opportunity to work with. So if you recognize people on here, if you don't recognize people but see their names, if you ever run into these folks at conferences, chat with them, because these are really good people trying to help advance lunar science. Some of them are very notably active in League, amongst other places. So one of the jobs we had in the Decadal was to identify these large missions and prioritize them. And so going into the Decadal, there were a bunch of sort of grandfathered in mission concepts, things that had been done in the past that we could consider. There are also a set of pre-Decadal mission concept studies that were done by NASA, including things like a lunar geophysical network concept study, a Mercury lander, Intrepid, which is a long-range rover, and in situ geochronology. And then in the Decadal Survey, we had the opportunity to request a small number of additional concept studies if we thought it was valuable. And we ended up doing Endurance and also another lunar rover called Inspire. And these two, you'll notice these are both rovers. This actually highlights the central importance of the Intrepid mission concept. Sorry. So Intrepid was this concept run by Mark Robinson out of ASU for a very long range rover going about 2,000 kilometers on the near side of the moon. It would explore the moon's magmatic history. So lava flows, it would go through magnetic anomalies, through near young craters, some very young volcanic deposits, and explore them in great detail. And this mission concept was very interesting, both from the science, but also from the capabilities of this rover. This idea of going 2,000 kilometers is just transformative. We've never done that on another planet, going that far. And so a natural question that one could ask, and that we did ask, was, what if we took this capability and applied it elsewhere on the moon? And that led to endurance. And so it also not only led to endurance, which is shown here. So these are the Intrepid rovers. They actually designed a nuclear powered and a solar powered version. We designed two versions of endurance, one that rendezvoused with a robotic sample return vehicle and one that rendezvoused with astronauts. But it also led to that polar volatiles rover concept, where we basically stuck two giant drills on the rover to drive deep into PSRs and grab samples. And ultimately, the Decadal Survey picked one, Endurance A, the one shown here, as the highest priority. So going back to my little cartoon of the moon with all these different terrains, you can start playing games like, okay, we have a 2,000 kilometer rover, what could we do? And you could do something like this, where you land in one site, traverse a huge amount of distance, go to every different terrain that you could imagine, and in the case of endurance, then drive all the way down to the South Pole and meet up with Artemis. And the entire way grab samples. So you can just see how quickly this sort of capability could lead to transformative science. So yeah, endurance is a concept. This was the cover art. It would drive all the way down to the South Pole, would rendezvous with Artemis astronauts to return samples to Earth. And just to give you a sense of scale for this drive, 2,000 kilometers, it's a huge number, but it's also on the moon, and we don't have good intuition. I tend not to have good intuition for distances on the moon. So I made this little schematic diagram that I show when I go to places in DC to highlight the sheer scale of the distance. So here's the National Mall. NASA headquarters is down here somewhere. And one of the first or early Artemis missions, they will have the capability to land, and astronauts can walk about 2 kilometers away from the lander. So the scale of the National Mall is roughly the scale of what you could explore with a single crewed mission. If you zoom out to all of DC and Maryland and Southern Maryland and Northern Virginia, you can sort of draw a circle. This is the size of Shackleton crater, so a large crater, or it's actually a fairly small crater by lunar standards, near the South Pole of the moon. And you can imagine that if you had a pressurized rover, you might be able to drive something like this, some sort of scale like this. Endurance is zooming way far out. So here's DC. Endurance is like driving from DC to Chicago through the Appalachians, not on a highway. And so you can get a sense here, or at least I think this helps illustrate the sheer scale that we're talking about. So here's the rover that we actually designed during the Decadal Survey. This is a pretty large rover. It's 500 kilograms. It's about 3 meters tall, or 2.7 meters tall. So this is taller than an astronaut, fully suited. But the key to this rover and to Intrepid and all the Intrepid's various related rovers is the mobility system. Is you need this rover to be incredibly autonomous. It needs to drive fast by rover standards. So the top speed on this is 1 kilometer per hour, which is very slow by human standards, extremely slow by driving standards. But most rovers, planetary rovers, do not drive this fast. They drive probably an order of magnitude slower. This is the max speed, but on average, it doesn't actually drive that fast. And we designed it to have these sort of mesh compliant wheels like the Apollo lunar rover, and capable of driving over moderate slopes. One interesting thing is, even though we're on the far side driving across this sort of rugged terrain, you can design traverses that never go on very steep slopes. So we drive from the middle of SPA through some large basins, in and out of Schrodinger crater, like down its rim, and we never exceeded slopes of about 13 degrees. So you can do this drive pretty reasonably. We designed it to do this all in 4 years. And there are a variety of other interesting aspects, like we have a pretty large communications dish here. Because we're on the far side, we have to communicate via a relay. Here's another view of the rover with its arm outstretched, and you could see it would scoop up sample with the arm, and it would deposit these in 12 canisters that would be attached to the side of the rover. As for science instruments, the original Endurance concept is like a Swiss Army knife of different scientific instruments. And that's because it was actually one of our ground rules. We said it had to have the Intrepid instrument suite, because we thought that that was a very capable in situ geology package. So I would fully expect that these instruments will change, especially as the requirements get set. But we had imagined things like having imagers and spectrometers, geophysical instruments like a magnetometer, accelerometer, things that could measure composition, uh, like a gamma ray spectrometer or APXS on the arm, all sorts of things. So the idea and the concept was that this could do a lot. But the biggest challenge for this is really the drive. So, and really doing it autonomously. So on the moon, we have to drive without roads, obviously, without GPS. So you have to figure out where you are on the moon using different methods. We don't have images at the resolution that you would have, say, on Earth at street view level. So you can't like pre-plan every single little boulder ahead of time. We have very good LRO data covering the entire traverse at sort of half meter per pixel scale, which is good because the rover can basically drive over anything at half meter per pixel. But importantly, the rover has to do it all on its own. So here's my last panel. Is there are a variety of autonomous cars out there these days, and if you get stuck in an autonomous car, or if your little food delivery robot gets stuck, someone can go out and fix it or move it. Or with the Apollo lunar rover, with the astronauts driving around doing very sporty things as astronauts do, they can get out and fix it and move the rover around. But if this rover gets stuck, that's potentially the end of the mission. You have to be very cautious about making sure this thing can do the drive. So a good example here is Lunokhod. Lunokhod 2 was a lunar rover built by the Russians, and it ended up accidentally getting dust on the surface of the radiator, and that dust led to the rover overheating, and it was the end of the mission. And so if you have a mistake, it's very easy to have fatal mistakes, and you have to plan to avoid them. I'll actually skip that. So why are we doing this long drive other than taking all this great data? It's really about grabbing a lot of samples along the way. So we would stop at 12 sites nominally, grab 200 grams of samples at a minimum. But in practice, we're actually designing the rover to be capable of returning a huge amount of sample. We designed it to carry about 100 kilograms total, which is comparable to like Apollo 17. So this is a lot of mass, with the idea that you could use all that material to do all the laboratory analyses that you need to answer those motivating science questions. And this idea of having a lot of mass is really important. And it's something that resonated within the Decadal Survey. And this is a slide that Sonia Tiku helped make, basically saying that more is actually better. Which might be obvious, but it's useful to think through, why is it actually better? So if we had just a small amount of mass, say a kilogram or 2 kilograms, which is about what you can stick in a robotic Earth return vehicle like OSIRIS-REx or Hayabusa, you're getting a very small amount of material, probably from only one location. NASA is going to withhold about 50% of that material right off the top. It's going to put that in long-term curation. You don't get to touch it. That's good for future scientists, but it means that you're reducing the mass that you have to actually answer the questions up front. And so you end up in the scenario where you question how much science would you not be able to do if you had a small sample mass? Or if you're limited in sample mass, how many reproducibility studies would you not do? If you only have a small number of rocklets, you can't afford to do the same study multiple times to know that you've answered the question confidently. And this last one, if you have very limited samples, you're going to give them out very sparingly. And so how many people would not be able to analyze new lunar materials because of that? So the idea of having a huge amount of mass is really important because it lets you do all these things. You can imagine sending your samples out to more and more and more people, do more and more things, both reproducing studies, doing completely novel experiments, and it just enhances everything. So everything I've talked to you up to this point is really stuff that we did during the Decadal Survey. Since the Decadal, NASA has tasked JPL with sort of expanding on the Endurance mission concept, sort of finessing the costs, looking at. And so there's been some work happening in the last year or so looking at this. So for example, here's a little updated render of the rover as it currently sits in some JPL computer. And really the key thing that NASA is asking is to figure out how to reduce the cost of this rover. So in the original concept study, this was a sort of a New Frontiers class, billion-dollar class mission. And as you all may know, NASA's budget is particularly tight right now. And so figuring out any way to save money is desirable. So things like simplifying the mobility system a bit, removing instruments is a way to save money. But they've also asked us to do new things like making the rover serviceable by astronauts. So you can imagine as the rover gets down to the South Pole, astronauts could go and, I don't know, replace a tire or do other things, swap out instruments to let the rover go on and have extended missions. We also have been looking about whether you could do this rover with a fully solar version, which leads to this weird Viper-like, Roman chariot-like version where you have solar panels on the sides because you're going down to very low or very high latitude where the sun is low on the horizon. And you could probably do this. There are some pretty notable cons if you go fully solar. So Endurance in the Decadal, it was this mission concept that we produced. And I said that Decadal ultimately recommended it. I'm going to explain what that means is they actually said down here, this third bullet, they said to NASA that Endurance should be implemented as a strategic medium class mission and the highest priority of NASA's lunar program. So I'm going to explain what some of these words mean. So strategic, that means it's a mission that is high enough value that it's just asserted as you must do it. Another synonym that sometimes uses directed mission. It's basically NASA is directing to some lab or some group of labs. Thou must build Europa Clipper, for example, was a strategic mission or is a strategic mission. Medium class here, that's telling you something about the cost. This is sort of New Frontiers billion-dollar class-ish, so it's a expensive mission, but it's not the most expensive mission, or even close to the most expensive set of missions, which are multi-billion-dollar missions. And then this is the highest priority of lunar discovery and exploration program, which is sort of separate from many of the other parts of NASA. So lots of fun praise about the idea that this rover could grab all these samples across all the terrains. That's actually transformative. And there was a lot of excitement about trying to couple robotic exploration with human exploration. The idea that this could rendezvous with astronauts and the two things could work together to accomplish science was viewed as very valuable. So what's next? What's the road ahead of Endurance? So I've been talking all about this mission concept and the Decadal. I'm going to put it on timeline just to help provide some context. So the Decadal went from 2020 to 2022. The endurance concept study was only a few months within that. So we basically did this whole engineering study in the span of like 3-4 months. The Decadal Survey came out. NASA said, oh, great, you wrote a Decadal Survey. We're going to look at it. And in the last year is when things have started to become more real, where NASA has asked JPL to do follow-up studies. We at JPL helped organize and run a public science workshop that was in August. I need to move the today bar all the way to the end of 2023. But the thing that's likely to come up soon is that NASA is likely, they've said that they are going to form a science definition team for endurance. And science definition team, or SDT, is really important because that's the group that will set the more specific requirements for the rover. So for example, where do we actually need to go? Or what measurements do we actually need to take? What are we required to take? And that this is sort of the first step in what might ultimately become, say, a competition for the instruments and a more thorough design of the rover. And this is just like a little snapshot of today, or the last few years. This is part of a much larger timeline where we can go back decades looking at past mission concepts, of which endurance is only the most recent, looking at South Pole-Aitken Basin, and going forward in time. And I haven't said when this thing would launch, but if it were to launch, it would be sometime in the early 2030s. So in the concept study, we assume 2030. Given NASA's budget, it's probably going to be pushed out a little bit from there. But we're talking about a mission that's many years away at this point. So I mentioned we had this workshop, which we're working on a final report still in draft format right now to come from this. But this was a fun example, and I know many of you got to attend, which was great. Just to show little highlights, this was a hybrid workshop with a lot of attendees. But of course, everyone's favorite attendee was the rover. One of the commercial companies that is interested in building lunar rovers brought their test bed. This is Astrolab's Flex rover. And they drove it around on campus and showed it off. So that was fun. But it's a good example that commercial rover is something very interesting and very different for planetary missions at this scale. So right now, NASA is very invested in having commercial led or commercial partnered activities on the moon. So that includes things like we have all these commercial landers, the CLIPS program. So that's these top two are CLIPS landers. Also, this bottom one down here is a CLIPS lander delivering a NASA rover, Viper. This includes the human landers, so the Blue Origin and SpaceX HLS landers. It includes even the space suits that the astronauts are wearing. Those are commercial contracts. And so right now, the moon is a very different environment where commercial partnerships are really leading the way. And there's a lot of interest right now about whether this mission, this long-range rover, could be done either as a commercial service or in partnership with commercial companies. So a lot of this discussion is happening right now, particularly because there's a lot of companies right now that are proposing lunar rovers for Artemis, for the crewed rover. So these are things that astronauts would drive. Here's that Flex rover with astronauts on it. But a bunch of companies are proposing this. And there's a lot of interest in taking rovers like this, things that would become the Lunar Terrain Vehicle, or LTV, and sort of either making a second copy or taking parts of it and spinning it into endurance. And this is very interesting because this is not how large planetary missions are usually done. So it'll be very interesting to see how this shapes up in the next couple of years. So this is my last slide. So endurance is a concept for a long-range rover that would go to South Pole-Aitken Basin on the far side of the moon. It's the highest priority from the new Decadal Survey for the NASA's lunar program. And NASA seems to be taking that recommendation seriously and has been doing follow-up studies and looking to continue development of the rover. So what are the next steps? What are the things to be aware of? So NASA is planning this SDT. So that's something that people may be able to apply to join in the next year. Now is also the time to start thinking and particularly publishing. What are the kinds of science that you would like answered on the far side of the moon in South Pole-Aitken Basin? This is a great time to put out hypothesis papers, to think about what measurements you need to answer questions. That way, as the rover gets designed, it can react to those scientific developments. And also, this thing will eventually have to fly instruments, and so it's a good time now to be thinking about what those instruments could or should be. And so with that, I'll stop sharing and we can do discussion.
Thanks so much for that, James. That was great. I think we do have a few questions in the chat actually. So we'll work our way from the most recent, the least recent. I'll read out your name, and if you want to unmute and ask your question, that's an option, or I can read out your question. So the first question is from Hanal Modha. So Hanal, if you want to unmute and ask your question, please go ahead.
Hi, James. It was really nice talk.
Thank you.
Hello. Yeah,
I hear you.
And I have two questions. One is, what would be the most cost-effective mission, like a complete robotic mission for sample return thingy, or a human landing mission with sample? What would be, as you said, that NASA has tight budget, so
Yeah, so that question was actually one of the things that we tried to answer in the original concept study, and I didn't really talk about it. But
Okay.
one of the goals in that concept study was to actually say, let's send a rover to the far side and collect samples. But what is the cost difference if I have it drive all the way to the astronauts and drop off samples, or if I send a second robotic Earth return vehicle and bring the samples to that thing and it launches them back to Earth? So what's the cost difference of doing this all robotic in the sort of usual way that Planetary Science does its missions, or leveraging the humans on the surface of the moon? And basically, by going to the astronauts, you save $1 billion. So that's basically how much it costs to build that robotic Earth return vehicle. Now, Artemis is not cheap. It's not cheap to get astronauts to the surface of the moon. And so it's not quite apples to apples. But if we can partner with humans, it lets us do a lot more science. And I think that's something that is really important to Artemis. And so that's why this one ended up leveraging humans as part of it.
Okay. Yeah, I got it. And another question is, as it is a biggest impact on the moon, right? So, and it was also happened in the very early stage. So, what's your opinion on like how it has affected lunar rotation, tilt, and axis?
Yeah, so this is
As of now, I'm sorry, as of now, we are saying it is on the far side and near to South Pole, but there may be possibility that it has rotated on a very different angle.
Yes. So this is actually much closer to my actual field of research. I do a lot of work in rotational dynamics and true polar wander. And so we have, I think, very good reason to think that South Pole-Aitken did not form where it is today, that it actually formed more likely at basically higher latitude closer to the equator, and that the moon reoriented, had true polar wander to place it closer to the South Pole. But it probably also did all sorts of other weird things, like the impact itself probably impacted enough angular momentum and change in the moon's structure to put it in a period of non-principal axis rotation. So it might have unlocked from synchronous rotation and spun around for a while before relocking. So SPA probably had, of really anything on the moon, probably the single largest impact on the moon's rotational dynamics through time. So, which I think is kind of fun.
Yes, and do you have like, I don't have any idea if anything published on this question, it was a tilt impact or it was on-head impact?
Yeah, so there has been some work trying to figure out the direction in which the impactor came in. We suspect because it's fairly elliptical, it's elongated north-south, that SPA formed from an oblique impact. But there's argument in the community about whether it came in from the south and shot its ejecta to the north, or came in from the north and shot its ejecta to the south. That's why I didn't explain the orientation of that animation and which way the ejecta was going, is because different people argue different ways. I personally am the fan that it ejected its material to the north, so it came in from the south. But that's something that people debate based on the available data.
Okay, thank you so much.
Sure.
Okay,
Great,
so
thanks. Oh
oh.
yeah, you go ahead, Hunter.
I had a question next, but that is less instrument specific and I think less relevant for right now. So if we get to it at the end, that's fine. But it looks like next comment is on with the speed of the rover, the kick up of dust would be a bit of a headache for the rover and instruments. So I'm wondering if you have any comments related to that. And this kind of ties into the next question about by Parker Bradshaw, last one was by Zhu Wang, and the possibility of a successful 2,000-kilometer traverse.
Yeah, so we are a Ferrari by rover standards, but we are I don't know what the appropriate analogy by like human driving standards are. We are, even though we're fast compared to say Perseverance and Curiosity, which drive basically an order of magnitude slower, we're still creeping along on the moon. Like it was on a treadmill the other day, and for fun I put it at 1 kilometer per hour, and you are crawling along at that speed. So you actually don't kick up a lot of dust at that speed. And one of the things is, well, you do kick up some dust, but the rover was actually purposely designed to be high above the ground. So much so that as you're driving it, if you were to drive at 1 kilometer per hour, you don't have enough energy imparted into material to throw it up high enough to hit the instruments. And the bottom of the rover is like, I don't know, it's almost a meter off the ground, and the instruments are higher than that. So it's something that we aren't worried too much about throwing dust up there, but lunar dust and charging of the surface is always something that's a challenge for the moon. I mean, dust is also annoying for, say, the wheels themselves, and we have to have wheels that can survive such a long time, actuators that can survive such a long time. So it's something that I think a lot of money will be spent trying to make sure that we don't have a problem, or at least mitigating the problem. What gives you confidence about traversing 2,000 kilometers? Yeah, endurance would have to go 500 kilometers per year versus Mars going about tens of kilometers per year. It is an order of magnitude more than an order of magnitude increase. It's something that basically we have all the pieces to do it. Like we have there are some challenging parts of the whole system, like making sure that you have wheels, for example, that can drive on lunar terrain and lunar temperatures for that long. That's one part of the equation that's a little rougher. But things like the autonomy, that, like, we have the algorithms already. Like we do them on the Earth already, both for in commercial cars, but also like there are Department of Defense things that drive around off-road going like 50 kilometers per hour, so, or faster. So it's really about putting all the pieces together and doing it in a space environment. So that's something that in the concept study we spent a lot of time developing sort of a technology plan for what you would need to do and when to make sure that you could fly this mission. It's not going to be easy, but it's something that appears tractable. And we have all the pieces, we just need to put them together in the right way and make sure we test to the point that we know we can do it. But it is completely different. We've never done this before on another planetary body, so I'm sure there will be hiccups along the way.
So thank you. I have a question now regarding, so it seems like given the kind of speed and distance traveled, the instrument suite is more focused on things that can take data as the rover is moving versus stopping a lot and pressing something against the surface of a sample to try to get some more detailed analysis about it. And so I'm wondering what you think the necessarily motivation or prioritization of instruments on the rover will be moving forward, and whether you could see that changing or kind of a cadence of deciding where to sample versus stopping to look at something more closely, just driving.
Yeah, no, this is a great question, and it's something that we had some discussion about this at the science workshop, and I think it's something that it really kind of needs. I want a lot of scientists to be worried about this question, because endurance as a concept only works if you can get your samples to your drop-off point in 4 years or 3 years. So you have to prioritize speed, because if you stop and do like opportunistic science all the time, you'll slow down a lot, and it's very easy to run out of time and start adding years and years to the mission, which is bad both from making sure that the rover survives, like an engineering perspective why it's bad, but really the reason it's bad is because every year costs a lot of money, and you cannot like we are so strapped for cash. We have to be as cost effective as possible. So I think there will always be this driver to be doing things fast, but just because you're doing things fast does not mean it's an excuse to blow off all the science that we kind of need to be doing that got this mission sold along the way. So there are certain types of investigations that probably wouldn't be highly prioritized just for that reason. So for example, so there was a comment by Terry Fong about Viper going Viper's top mechanical speed of 0.7 kilometers per hour, and its speed made good is really slow, like a centimeter per second. And if I recall, one of the reasons why is because they're doing gamma ray neutron spectrometry measurements the entire time, and they need to be going slow so they can actually integrate. And so there are types of measurements that actually slow down the rover, either because you have to go slow to do them, like in the case of Viper, or in endurance, we also had a gamma ray neutron spectrometer that we didn't have on, or I don't think we had on while driving, but we would park and stop and like integrate for half a day or 24 hours, 48 hours. And every time you stop for that long, it just kills your time. So I think that there will be a push from the sort of engineering cost side for things that can be done quickly, like taking remote sensing observations, like taking pictures, taking spectra, maybe even doing things with the arm and interacting with the surface, but it has to be done in a way that's quick. And you might build in budget, like scheduling margin that you can use for occasional opportunistic science. Like I always think of that example of the Apollo 17 orange glass, the orange soil. Like they weren't expecting it. They were walking around, driving around, they stumbled on it. And that glass was really important scientifically. And so you kind of want to have that ability, but you can't be stopping every kilometer and adding time because you just don't have it. So this is a long-winded answer that I don't know if it gave a terribly complete answer, but it shows the kinds of discussions that have been happening and kind of need to be happening in more detail.
Great, thank you.
I think we have a question from Melissa Roth. Melissa, if you want to unmute and ask a question, please go ahead.
Yeah, so along those lines, and pardon me, I was interrupted in the middle of your explanation, so I could have missed this. But with the prioritization on speed due to time constraints, will most of the samples be collected as like surface scoops? that can be done on brief stops, like very brief, or are you going to do those type of sampling on those more sporadic periodic stops and have it collected then?
Yeah, another great question. So I'll explain what the current plan is and then how it might change. So in the original concept study report, which by the way, it probably flew by, but the endurance report is all public, and I can share that link if I can find it in a sec. But in the original concept study report, we basically said we're going to go to 12 sites. 12 was picked for a scientific reason, but also a technical reason. And we're going to grab basically scoop samples or rake samples. We wanted rocklets, so things larger than a centimeter or a few centimeters to do a lot of the sample science, like geochronology. But we also did want regolith fines, so just sort of bulk samples of regolith. And we basically said, okay, for those 12 sites, let's assume we get an entire lunar daytime period, so about 2 Earth weeks. And we can have humans in the loop, and they help figure out where we scoop and what we store. And all that is done at the direction of science. Now, that's what was in the concept study. I think what an important task for the science definition team in the coming year or years is to see if that's actually sufficient. So the 12, I could explain where the 12 number comes from, but you could imagine maybe we want the opportunity to take lots of opportunistic samples along the way. And maybe we want hundreds of samples. I'd rather have hundreds of smaller mass samples, lots of a little samples versus a few large samples. You could make that trade, and it would probably impact how you design the sample caching system. So like we opted for just basically really simple boxes on the side of the rover. If you are collecting now, let's say 100 samples, or several hundred samples, like every couple kilometers, just grabbing something, then you've got to complicate the storage system because now you're storing lots of things. Or so maybe you need hundreds of boxes, or maybe you live with mixing your samples together in larger boxes, which seems scary to me. But that's an example of a trade that it's the science side of things. We need to figure out what we need to answer the questions and sort of work with the engineers to figure out what's possible. And there's been discussion about other like methods of collecting samples. Like every once in a while, people will bring up the idea of drilling, like taking cores out of boulders or that sort of thing, which wasn't in the original concept study. I personally am not a fan of doing that because it very quickly complicates the sample collection system. And I also think on the moon, like coring rocks is not necessarily the most necessary because the moon is already breaking everything up and mixing everything around, which is different than on Mars. I mean, Mars still has impact gardening, but you also have different geology operating on Mars that leads to a very different caching system. So, but these are things that I think the SDT will need to figure out. And so like if people here have really good ideas about that, that's something to be thinking about now. Like if somehow some assumption that I've said or that's in the report or that you see floating around is wrong, now's a good time to course correct us on that.
Great, thanks. If anyone has any other questions, please type them into the chat. We probably have time for maybe 1 or 2 more. In the meantime, while we're waiting for people to ask any more questions, I have one question, James, and was kind of like spurring why we wanted to have this event was since endurance is a long-term kind of mission, how can early career people who are early career right now get involved in the mission, maybe even the SDT, because, you know, it'll be a mission that is happening like during our careers as we kind of transition into more mid-career.
Yeah, no, that is a great question. So it's something I think right now we just have to be very vocal about. I say this because I am also technically early career too. um, the SCT has not been, even like the format of the SCT has not been decided. And I think something, I mean, when I am passing things up the chain, I think what could be an interesting way to deal with this for the SCT sake is either figure out, okay, can the SCT like accept white papers from people, or so like have a lot of input, like be open to all the input, even if people, the SCT itself is a small group of people. Or what I think would be more interesting is if the SCT included at least one early career representative on it. The way these SCTs often operate, like if you look back at past SCTs, they tend to be mid and late career people. And there are reasons for that. Like they want people who know what they're talking about, and that the result will be respected by the rest of the community. It's almost a perception game. But there's also a weird thing where they want the SCT to not be too self-serving. So like if it's late career people who aren't going to be proposing their own instruments, that helps them theoretically be more unbiased. At least that's what some folks have said. I think that's arguable whether that is actually true, but I think right now is a great time for all of us, say at League, at LPSC, at town halls, these sorts of things, to bring this up, because yeah, this is a mission that it's not going to get there for 10 years. So all the early career people now are going to be mid-career people by then. And it's good to think of how we can incorporate early career folks in the mission development at an early stage. And this is something that's happening also with like Uranus right now, like Uranus Orbiter Probe. They're thinking about this, but it'd be good to also to tap into whatever there's existing programs for some of the missions trying to incorporate more early career folks and also more folks from diverse backgrounds, diverse institutions. Be interesting to think through how we can actually do that in endurance at this early stage.
Awesome, thank you. And now we've hit the top of the hour, so I just want to thank our speaker again, James. Thank you so much for giving us the quick overview of endurance. It looks like a really awesome mission, and we're excited to see what comes next for the mission. And I just want to thank everyone who attended and who asked questions. We'll probably be having another event at LPSC. Look out for the announcement about that. It might be in person, it might be virtual, we're still deciding. But yeah, thank you to everyone for attending, and thank you, James.
Yeah, well, thank you for having me. And if anyone has follow-up questions, feel free to shoot me an email. I'll be at AGU, I'll be at LPSC. Don't hesitate to say hi. I'm sure we'll be presenting endurance stuff then, and this will be something we'll be talking about for a long time. So thank you for having me.
Thanks.